A gas turbine, also a combustion turbine, is a type of continuous flow internal combustion engine. The main parts common to all gas turbine engines from the power producing part and are in the direction of flow. A rotating gas compressor, a combustor, a compressor driven turbine. The basic operation of the gas turbine is a Breton cycle with the air as the working fluid. Atmospheric air flows through the compressor that brings it to higher pressure. Energy is then added by spraying fuel into the air and igniting it so that the combustion generates a high temperature flow. This high temperature pressurized gas enters a turbine, producing a shaft work output in the process, used to drive the compressor. The unused energy comes out in the exhaust gases that can be repurposed for external work, such as directly producing thrust in a turbojet engine or a rotating second independent turbine that can be connected to a fan, propeller or electrical generator. The purpose of the gas turbine determines the design so that the most desirable split of energy between the thrust and the shaft work is achieved. The fourth step of the Breton cycle is omitted as gas turbines have open systems that do not reuse the same air. In a real gas turbine, mechanical energy is changed irreversibly into pressure and thermal energy. When the gas is compressed, heat is added in the combustion chamber and the specific volume of the gas increases, accompanied by a slight loss in pressure. During expansion through the stator and rotor passages in the turbine, irreversible energy transformation once again occurs. Fresh air is taken in place of heat rejection. Air is taken in by a compressor called a gas generator with either an axial or centrifugal design or a combination of the two. The air is then ducted into the combustor sector, which can be of a annular can or can-annular design. In the combustor sector, roughly 70% of the air from the compressor is ducted around the combustor itself for cooling purpose. The remaining roughly 30% of the air is mixed with the fuel and ignited by the already burning air-fuel mixture, which then expands, producing power across the turbine. This expansion of the mixture then leaves the combustor section and has its velocity increase across the turbine section to strike the turbine blades, spinning the disc they are attached to, thus creating useful power. Of the power produced, 60 to 70% is solely used to power the gas generator. The remaining power is used to power what the engine is being used for, typically an aviation application, being thrust in a turbojet, driving the fan of a turbofan, rotor or accessory of the turbo shaft. If the engine has a power turbine added to drive an industrial generator or a helicopter rotor, the exit pressure will be as close to the entry pressure as possible, with only enough energy left to overcome the pressure losses in the exhaust ducting and expel the exhaust. For a turboprop engine, there will be a particular balance between propeller power and jet thrust, which gives the most economical operation. In a turbojet engine, only enough pressure and energy is extracted from the flow to drive the compressor and other components. The remaining high pressure gases are accelerated through a nozzle to provide a jet to propel an aircraft. The smaller the engine, the higher the rotation rate of the shaft must be to attain the required blade tip speed. Blade tip speed determines the maximum pressure ratios that can be obtained by the turbine and the compressor. This in turn limits the maximum power and efficiency that can be obtained by the engine. In order for tip speed to remain constant, if the diameter of a rotor is reduced by half, the rotational speed must be doubled. For example, large jet engines operate around 10,000 to 25,000 rpm, while micro turbines spin as fast as 500,000 rpm. Mechanically, gas turbines can be considerably less complex than reciprocating engines. Simple turbines might have one main moving part, the compressor shaft, turbine rotor assembly, with other moving parts in the fuel system. This in turn can translate into price. For instance, costing 10,000 or for material. For jumbo 4 proved cheaper than Junkers the piston engine.